Alright, in this video we're going to solve just the first few steps of the strong-weak titration. So again, what we've done is we've set the table up already. The first step, we have added no base, so we've made no conjugate. We have 0.015 moles of the acid. Now if this were a strong acid, we could directly take the negative log, but it's not. What that means is we have to do an equilibrium problem. So we're going to have our weak acid react with water. It'll make hydronium and the conjugate base. Ka for that we know is, I'll write it up here, 1.8 times 10 to the minus fifth. That was given in the original problem. So I know that much. So now what we say is, alright, although the stoichiometry, the subtraction problems all through this table are done in moles, equilibrium is done in molarity. So I need to have a concentration here, not a moles. So concentration of this is going to be 0.0150 over 0.100. Now I could do that math, but I'm not going to bother because my calculator can handle the math for me. So that's my starting concentration, and I don't have anything here. So these start as zeros. If these are zeros, then the reaction's not at equilibrium. It's got to go to the right because that's where the zeros are. So rather than making a full ice table, I'm going to go directly here. I know that this is going to be minus x, that's going to be x, and that's going to be x. So I'm going to end up with x squared over 0.0150 over 0.100 minus x is equal to 1.8 times 10 to the minus fifth. And I can plug that directly into my solver function. So I go math 0, go up, clear what I had in there. So what this is x squared divided by 0.010 divided by 0.1 minus x, end the parenthesis, and then subtract the value of k. Put in a really small guess, hit solve, and it's 0.00163. Just to be sure, I always get in the habit of exiting out, x enter, so my x here works out to be 0.00163. Now what's x? Remember that x is the concentration of hydronium, which means that the pH, get this out of my way, the pH is going to be the negative log of x. So on my calculator I can just go negative log x, and it's 2.79 is the pH. The next step works very similarly, but it's slightly more complex. Again, my weak acid is going to react with water. It's going to make hydronium and the conjugate base. This concentration, 0.0147 over 0.101. This concentration is 0, but this concentration is not, because I made some of the conjugate base. So the starting concentration here is 0.0003 over 0.101. This, of course, is still 0. So, am I at equilibrium? No, because I have a 0. What direction is it going? To the right, because that's where the 0 is. So this is going to be minus x, this is going to be x, this is going to be plus x. So now my equilibrium problem is more complex. Rather than being x squared on top, it's now x times 0.0003 over 0.101 plus x all over 0.0147 over 0.101 minus x, and that's equal to Ka, again 1.8 10 to the minus fifth. So if I decide to plug that in, I'm going to put that in my solver function. I think you can see the screen there. Go up, clear out what I had in there. So it's going to be x times 0.0003 divided 0.101 plus x. That's the top. That's divided by 0.0147 divided by 0.101 minus x. That's the bottom. Minus the value of k. Put it in. Make a guess for a small value. Solve it. And again, this is why I always like to x out. I can't see the power of 10 here. So I'm going to quit out. X equals 7.09 times 10 to the minus fourth. So x works out to be 7.09 times 10 to the minus fourth. Once again, what we found is the concentration of hydronium. So the pH is going to be the negative log of that. The negative log of x works out to be 3.15. Same basic process here. So the 10 and the 48 work exactly the same way. These numbers, of course, will change, and so the results will change, but the process for 10 and 48 is exactly the same as the process here. So I'll write it out, and then I'll put that in the next video just so you can see it.